Now we will have Alfonso García-Parrado, and he will talk about calculus in vector bundles using xAct and its applications to Yang-Mills theory.
Okay, right. So, well, this presentation has two parts that you can see now in your screen. Well, before just explaining each of these two parts, well, let me just mention that I have been using xAct for almost all of my career, and I found it I have found it very useful. And okay, if you are interested in doing involved tensor analysis computations, I think xAct is definitely for you. And one of the parts of the system that I find very important is the part of the system that deals with vector bundles, because this is the kernel for example, the spinor calculus package that has already appeared in Juan's talk, and also it can be used to implement, for example, Yang-Mills equations. So what I'm going to do is, well, this talk is divided into two parts. In the first part, I will just review the implementation of vector bundles in xAct, and then in the second part, as an application, I will illustrate how the Yang-Mills equations with no matter content can be implemented in xAct. Okay, so right. So let me just start. Well, I start here by reminding the mathematical definition of a vector bundle. We have a number of ingredients. We have the base manifold. We have the bundle manifold, and we have the projection of the bundle manifold on the base manifold. And then we have the so-called standard fiber, which in this case, since we are dealing with a vector bundle, it turns out that the standard fiber is a vector space. So as people, well, as those of you who have worked with vector bundles know, then this is basically mean that we have manifold that is split into disjoint sets that are the fibers, and these fibers are vector spaces. Okay, so let me just illustrate how this structure is implemented in xAct. Well, I need some preliminary code that I will be using. So okay, so we start by defining a dimension we start by defining a manifold of symbolic dimensions. So I need to start defining first the symbol that will represent the dimension, and then we define the manifold itself. Okay, so where are the ingredients of well, this definition defines automatically the most basic vector bundle, that is the tangent bundle of manifold. So if we check the list of vector bundles that we have now, we have we have just the tangent bundle of our manifold. Well, just to show you here how this is this symbol is represented. And okay, so we can check that all the ingredients of the definition of vector bundle are here for this specific bundle. So we have the base manifold of this bundle is the manifold M that we have defined. The dimension of the vector bundle is the dimension of the vector space fibers. In this case, it coincides with the dimension of the manifold, and we can. The fact that this is a vector bundle implies that we can attach a list of abstract indices to to it. Okay, so in this case, these are, well, I'm going to use Greek indices for as the abstract indices for the tangent bundle. So well, if I just go back for a second to the definition of the manifold, well, you can check that. Well, I said that vector bundle is automatically defined, and as the argument you are given the dimension, and you are you are given the list of abstract indices that we are going to use. Okay, so definition of a manifold gives us automatically all the ingredients to define the tangent bundle. But as you know, that if we want to do tensor analysis, we need, in addition to the tangent bundle, we need the dual of the tangent bundle. And then by doing tensor products of these bundles, we get the so-called tensor bundle. Well, one of the powers of this abstract index notation is that we don't need to define a new vector band, we don't need to define any of these tensor bundles, because these definitions are implicit in the list of abstract indices. And also, well, if we in physics, in addition to a manifold, we need a metric. Or in other words, suppose that our manifold is a space-time manifold, so we need to define a metric. And well, the metric automatically defines all the structures that you need. Well, the def command, well, you can choose to see this, whether you are going to see these structures by means of the def command, or you can just check these commands that tell you exactly what is automatically being defined when you define the metric. Okay, so we have well, the classic structure, the classic space-time structure. And right, so now let us define what is the topic of this presentation. Let us now define a vector bundle that is going to have the manifold M as its base manifold. But now what is going to be different is the standard fiber. So I'm going to define a standard fiber that is going to, well, I'm going to define a vector bundle whose standard fiber is going to be a vector space of dimension n. So first I define the symbol that will represent the dimension, and then I use xAct command to define the vector bundle. That is the vector bundle. And okay, so we can check that all the ingredients that are needed for the definition of a vector bundle are present. So we have the vector bundle itself, the vector bundle manifold, the base of the vector bundle. We have the dimension of the standard fiber, and also we have the list of abstract indices that as I said, well, this is the mark or the token that tells us that this is a vector bundle, that this is well, and also, as I mentioned, this abstract index notation saves us the work of defining all the tensor products of the vector bundles that we need to do tensor analysis. Right, now that we have the vector bundle, we want to do calculus in the vector bundle, and for that we need a linear connection in that. Well, it can be defined as a bilinear operator that takes sections that takes sections of the tangent bundle and 10 sections of the bundle itself, and returns a new section of the bundle. Okay, well, this is the mathematical definition. Okay, well, there are some extra conditions that I'm not detailing for lack of time, but everyone who is well, who is familiar with differential geometry knows Then okay, so I define the covariant derivative, and again a number of additional structures are defined that I summarize here. Okay, now I want to stress two of these different actually some of these different structures. On one hand, we have the Christoffel tensor of this covariant derivative that, well, is the usual space-time Christoffel tensor. And then, since this is a covariant derivative that has been defined in a vector bundle, we have what we call, or what is called the A Christoffel tensor. And okay, the Christoffel tensor is in xAct connection connection components are tensors, and the way in which that's achieved is that they are always defined with respect to a reference covariant derivative. In this case, if nothing is said, by default we use the reference the PD, which is a partial derivative with respect to a generic coordinate chart. So we have the Christoffel symbols, that is the usual Christoffel tensor with all its space-time indices, and we have also the what we might call the A Christoffel tensor, or internal Christoffel internal connection components, and here we have one space-time index and then two vector bundle indices. So we have two sets of connection components, and something similar happens with the curvature. We have two curvatures, the standard Riemann tensor, and then the vector bundle F curvature that we call F Riemann tensor. And you see, okay, Riemann tensor has the usual structure with all its space-time indices, and F Riemann has two antisymmetric indices, and then it has two bundle indices. Okay, so these are the definitions. And okay, so there are you can, as I said, you can do calculus with all these quant objects. And now I start with the second part of the talk, that is how this can be applied to a Yang-Mills theory. Well, for doing that, let me just remind you the background, the mathematical background of a Yang-Mills theory. And okay, the first point is that Yang-Mills theory in modern in the modern approach is formulated not in a vector bundle but in a principal bundle. So we have again a manifold and something which is the principal bundle, and we have the bundle projection. And now, rather than standard fiber as before, what we have is a Lie group. And okay, the situation is that we have G is a compact Lie group, that is going to be the gauge group, and G small g is its Lie algebra. Then we define a connection in what is the gauge connection in the principal bundle P, and it can be shown that this connection is represented by one form, that is a gauge a Lie algebra valued one form, and the curvature of the connection is given by this equation. And just in terms of this of the curvature of this connection, you can write down, you can obtain the Yang-Mills equation when you don't have any matter content, by means of this expression, where capital D is the exterior covariant derivative that is defined from the gauge connection, and star is the Hodge dual defined using the metric G. Well, okay, now in xAct, in xAct there is no implementation yet of principal bundles, but it turns out that for any representation of the Lie group on a vector space, we can define an associated vector bundle with base manifold M and standard fiber, the vector space V that we use for the representation. So what we can do if we want to implement Yang-Mills equations in xAct, we can just work with the associated vector bundle, and that is what I'm going to do next. Okay, since I have already defined a vector bundle, I'm going to use this vector bundle as to the associated vector bundle of some principal bundle in which a gauge connection has been defined. So what I need to do now is define a covariant derivative that is going to represent it's going to be the covariant derivative associated to the gauge connection that we have in the principal bundle. And okay, in this case, it has to be a covariant derivative that when acting on space-time tensors, it coincides with the usual Levi-Civita covariant derivative that we define along with the metric. Okay, so this is what basically this command tells us. Now I need to introduce a product that is going to represent the Lie bracket or that we need for the Lie algebra. And as Cyril already explained how this works, and I need to specify the constants of this product, and also this is going to be the correspondence between the connection one form that we have in the principal bundle and some field that is going to be defined in the associated vector bundle. So we are going to have a field, the so-called gauge potential in the vector bundle, and we are going to have the so-called field strength that corresponds to the curvature 2 form that we have in the vector bundle. Okay, so the Lie bracket works as expected. So that means that the gauge potential and the field strength are tensors, but are now are tensors with values are Lie algebra Lie algebra valued tensor fields. So it means that we can multiply them with the Lie bracket, and the canonicalizer knows the properties of the Lie bracket, right? So now I define the Lie group generators, the Lie group, the Lie algebra structure constants that are constants with respect to any covariant derivative, and of course they are scalars with respect to the Lie bracket product. And I just can write down the standard commutation relation of the Lie group generators. And also we have the Jacobi identity that we can the Jacobi identity translates into some properties of the structure constants that you can deduce doing computations. Okay, I'm not detailing too much these computations, but I think that anyone who is familiar with these things will recognize what exactly I am doing. And with these ingredients, I can define the components of the gauge field or the gauge potential in the Lie algebra basis that are now scalars with respect to the Lie algebra. So we get the standard expansion of the gauge potential in terms of the Lie algebra generators. Okay, and so we can just expand the Lie bracket, and there's something similar for the field strength, which again is a scalar, and also I have the expansion of the field strength in terms of the components of the field strength in terms of the Lie algebra generators. Right now we have the ingredients that we need to obtain the well. And there's something else that I have to do, and is since since we want to write down the Yang-Mills equation in some generic coordinate system, I need to introduce a generic basis in the vector bundle. This is done in this way. So this generic basis, you can think of this as a frame in the vector bundle. It's the Lie bracket of this generic frame is given by this expression. And I can express Lie algebra generators in terms of the frame. And the coefficients of the expansion are precisely the structure constants. And we can check that this is consistent with the Jacobi identity that was obtained before. I'm not detailing this computation just by lack of time, but I think that people familiar with this sort of computations should understand what I am doing, at least in a general vision. So right, so now I have I really have the ingredients. I define now the coupling constant and the covariant derivative that is compatible with the general frame. So meaning that the covariant derivative of the frame is 0. This is going to be an automatic rule, and the components of the connection and curvature are regarded as scalars with respect to the Lie algebra product. Now, any covariant derivative, any gauge covariant derivative can be expressed in terms of the covariant derivative that is compatible with the general frame. And I can now set up the relation between the internal Christoffel symbols that we have in the vector bundle theory and the gauge potential that comes from the principal bundle theory. And this is the relation, and something similar for the field strength. I can set up the relation between the field strength and the components of the curvature of the gauge connection that we have defined in the principal bundle. So then it gives me just obtain an expression of an expression. I'm just going to run the computation and explain at the end what this expression is. Well, this expression is again the relation between the field strength and the gauge potential that can be found in every textbook. And this is the expression that can be also written in terms of the gauge covariant derivative, covariant derivative that is compatible with the metric. This formula is obtained assuming that we are working in a frame, in a vector bundled frame, such that its spacetime part is holonomic, is a coordinate frame. Okay, so now with this expression, I can just take this expression and write down the Yang-Mills equation. Okay, so I just have to replace what I got in the previous slide and run the computation. And here it is. Here, you have the Yang-Mills vacuum equation fully expanded out in terms of the structure constants of the Lie group, the metric tensor, the gauge potential that you define in your vector bundle, and here you have the Christoffel symbols that you would get from your space-time background. For example, if you want to write down Yang-Mills vacuum equation in a Schwarzschild background, then you compute these Christoffel symbols, and then you could obtain this set of equations. Now, you could either give an ansatz to the gauge potential, that this is one of the things that is usually done, or you could try to solve this equation as a partial differential equation just by trying to find a hyperbolization of this of the equation. I will stop here and thank you for your attention.
Thank you very much, Alfonso. This was very interesting and a very nice introduction to vector bundles. Indeed, a very important part of how extensor and all of xAct works.